Okay, and for our final problem, we're going to move to something called a confidence interval. And let's explain what we mean by a confidence interval. A confidence interval is the idea that we want to be within a certain percentage certainty that the two averages are not zero. So the formula, a little bit different from the one in the book. I like using this one. I'm taking my average of our two pieces of data. I'm going to subtract them and add and subtract the z sub alpha divided by 2 times the quantity of the square root of our standard deviations squared divided by our sample sizes. So, I mean, what this does is it really quickly, in one stroke, tests whether or not we're inside of our confidence interval. And let's take a look at maybe some, two voltages of different brands of batteries. And we're going to look at we want to be 95% sure that these two batteries are the same. And our test is to see whether or not our mu sub 1 minus mu sub 2 is going to be equal to 0. Now, if we find that our answer to this problem has 0 in our answer, we're going to not reject the null hypothesis. But we find out that our confidence interval does not contain 0, then we're going to reject the null hypothesis. I'll say that again. This is the critical part. If we find that our confidence interval does not contain 0, then we're going to reject our confidence interval. All right, so here we go. The formula for the problem is written above, and we have these two brands of batteries. So we subtract our averages of the two batteries. It doesn't matter which way we do it. And then we're going to add and subtract from that this z-score right here. And the z-score, since we're looking at an alpha of 0.05, since we want a 95% confidence interval, we have to look at the two values that split alpha in half. Now, what's important is that a lot of people make a mistake and they'll go to 0.9500 and 0.0500, but that's not really what we should be doing, because since this is a two-tailed test, we have to look at 0.9750 and 0.0250, so that's going to be plus or minus 1.96. And then we can compute our square root with our standard deviation of the first set of batteries and are divided by the sample size. Notice that I had to qualify this with the normal distribution since the sample size was under 30. And then add to that our square of the standard distribution, or standard deviation, excuse me, divided by our sample size, 30. And then we get 0.4 plus or minus 1.96 divided by 0.003 or 3 thousandths, and be prepared to read scientific notation, 3/10,000ths. That's what your graphing calculator just told you if you did this along with me. Okay, so 1.96 times the square root of 33/10,000ths. That's 0.4 plus or minus 113 thousandths. Now, if I'm going to split this up into 0.4 minus 113 thousandths and 0.4 plus 113 thousandths, and that gives me an answer of 287 thousandths is less than mu1 minus mu2, which is less than 513 thousandths. Now, what I said before, and I repeated because this is important, that our 95% confidence interval is telling me that my average is between here and here. Now, do you notice that between here and here does not include 0? Since this does not include 0, it's both positive numbers, we're going to decide to reject the null hypothesis. We're going to reject that these batteries are the same, that these batteries are not statistically significant, but they are. These are statistically significant batteries. Now, granted, they were pretty close. I mean, you got really close to zero here and here, but there's still enough evidence to say that you would choose brand X over brand Y because they're better batteries. All right, that's been it. Send me emails if you have any questions.